What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question in 3.107, the textbook says this butterfly valve with a diameter of 12 feet is used to control the flow in a 12-foot diameter outlet pipe in a dam. In the position shown, the valve is closed. The valve is supported by a horizontal shaft through its center. The shaft is located at a height equaling 60 feet below the water surface. What torque would have to be applied to the shaft to hold the valve in position shown? First step is always determine the goal. The goal is to find the torque that has to be applied to the shaft to hold the valve in the position shown, which is the equilibrium position. Torque is the same thing as moment. So when it's asking for torque, it just says it's calculating moment. So calculating moment needed to keep it shut. To keep valve right? To keep valve shut, closed. We're given this whole diagram. We're also given that the diameter is 12 feet for the butterfly valve, which is this. I'm probably gonna start calling it a gate. So this butterfly gate has a diameter of 12 feet. And then we're also given that h is equal to 60 feet. So this depth goes directly to the middle of the shaft, which is also where the centroid is located. Because it's in the middle of it. The centroid of a circle will just be that halfway point. The same as a rectangle. So that's everything I need to write given down. We're also given this. It's important to mention this. We're given 30 degrees by the vertical axis. That'll be important later. So with these gate problems, there's 3 steps you gotta follow to solve these gate problems. And it's find pressure force, so FP. Second step is to locate the center of pressure. Okay, and then the last step is to calculate the moment, and which in this case is all we need to do to solve. So let's go ahead and do this first step then. So we're gotta calculate the force of pressure caused by this water. This water has a lot of weight. It's going to cause pressure on the butterfly valve. Also, I'm going to mention the butterfly valve. All that means is that there's like a little hinge right here in the middle, and the gates will basically have like 2 doors and they can open. That's all that means. I think it just means that the joint is in the middle and it can open either way. So the pressure force formula is pressure with respect to the centroid times the area. When we rearrange this, we know that pressure is equal to specific weight of the liquid, in this case water, multiplied by the height, and we need to do it to the centroid, so we put the bar over it. And the area, we need to find the area of the gate in this case, or butterfly valve. So that means we need to know the specific weight of water. We can look in the textbook. We're just going to assume a value of 62.4. I think that's what the textbook does, or my teacher did that. So we're going to assume a temperature of 50 degrees Fahrenheit so that we have a specific weight of 62.4 what is it? Pounds per feet? Yeah, pounds force. So therefore, specific water equals 62.40 pounds force per feet cubed. So we have that. The height is given to us. It gives the depth of the water to the surface to the centroid perfectly, so we don't have to do any calculations. So we know that. You gotta calculate the area of the gate. It's a circle because we know it's a circle because we're given the diameter. We know that the area of a circle is pi r squared. If you use a diameter, it's pi over 4 times the diameter squared. Put that in the calculator. You get a value of about 113.1 feet squared. So we can go ahead and plug all that in. If you plug it all in and put it in the calculator for each variable, you get the pressure force caused by the water on the gate is 4.234 times 10 to the 5th power pounds force. So that's our first step done. We need to get the second step done, which is locating the center of pressure. The formula to do that is the slant distance from the center of pressure to the surface of water equals the slant distance from the centroid to the surface of water plus area of moment of inertia over slant distance again from the centroid times the area, in this case area of the gate. So the slant distance, remember, the center of pressure is always going to be a little bit lower because there's more pressure the lower you go. So the centroid is where the shaft is. The center of pressure is going to be a little bit below it. So we know in this, when it says slant distance, it just continues on onto this 30-degree vertical angle all the way to the surface. So we know from this dot at that 30-degree angle to this surface of water, that's the slant distance of the centroid. And then same thing with the center of pressure, but it's just from here to the surface at that same angle. So let's start to solve for the center of pressure, the slant distance. We need to start solving for these variables. So let's go ahead and start doing that. The area of moment of inertia for a circle is pi over 4. Pi over 4r to the 4th power. We know the radius is just half a diameter. So that would be 6 feet. Half of 12 is 6. Put that in the calculator, you get that the area of moment of inertia is equal to 1017.9 feet to the 4th power. We need to find, we already found the area of the gate, and then we need to find the slant distance from the centroid to the surface of water. So we need to draw a triangle. So the triangle I'm drawing is representing right here. All the way to the centroid, right? So I messed up. It needs to be not to the bottom. Okay. So I'm drawing this triangle, and this is, right, this whole length from the centroid to the surface of water. That's our slant distance. This is our h value, which equals 60 feet, yeah. And then this is a right triangle, so we know that's 90 degrees. And we also have an angle. We have this vertical angle right here. It's 30 degrees. That says 30 degrees. So we know that that means this is also equal to 30, right? Some geometry rule, I can't remember it. But we know that it's the same line. We know that that's just going to be 30 degrees. So we need to find the slant distance. So we can use cosine of 60, some trigonometry. We know that's adjacent. No, not 60, 30. We know that we're using this angle. We know that's adjacent over hypotenuse. We rearrange it. We get slant distance equals 60 feet over cosine 30 degrees. Put it on a calculator, you get a slant distance of 69.28 for the centroid. So we have everything we need to solve for the center of pressure now. So let's go plug all that in, put that in the calculator. You will get a slant distance of to the center of pressure to the surface of the water of 69.28 0.41 feet. Let's go ahead, before we move on to the next step, it's always smart, because we'll need it when we calculate the moment. We're always going to need, not always, but most of the time, you're going to need the distance between the center of pressure and the slant distance from the centroid. And this is for the calculating of the moment for the next step. So let's just go ahead and do it real quick. So that will equal 0.13 feet. So now our last step, let's calculate our moment. Let's draw a little FBD real quick. This one's be really simple. This is our joint, or shaft, I mean. It also happens to be where our centroid is. And then our centroid we know is a little bit lower because the pressure is lower. We know that we just calculate the difference between these 2 points at that same angle of 30 degrees. And this is at 30 degrees. We know that's 0.13 feet. We know that the pressure force, mathematically, to help us solve the moment, acts at the center of pressure. And we need to calculate the moment about this shaft to equal the force of pressure to keep that gate closed, right? So we need to find the moment of the hinge or the joint or shaft, whatever it's called. So we know that the moment is just going to be this force multiplied by this perpendicular distance. Let's go ahead and plug that in. I'll write it out symbolically first. Plug those numbers in. We got put that in the calculator, you get 5.5 times 10 to the 4th pounds force times feet. And if we want to think about direction here of where the moment's going, we know that this force is coming this way, right? Because the water is on this side, so it's going to be on top. That will push this way, and that's counterclockwise. So we know that the force required, the torque required to keep it closed from a force coming this way will be going clockwise. So the direction will be this way. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.